Hello, so this is summary of lecture 25, symmetric and positive definite matrix. And here I will summarize everything that I learned from the lecture. So let's start right away. We're here interested mainly in the symmetric and real matrix. So let's right away give two facts about it. So symmetric, so real and symmetric matrix. So the first fact is that the eigenvalues are real, and the second one, the eigenvectors are perpendicular. Or a better word to say it is that can be chosen to be perpendicular. And why it is can be chosen? So, okay, let's say, the identity one, in this case it's real and it is symmetric and the eigenvalues are real and all of them are 1, but in this case it is repeated eigenvalues, right? And then you can imagine, so we have a freedom to choose whatever eigenvector we want. So if you imagine, the eigenvector will be like just a constant of ABC. So we have like a full 3D plane that we can choose as an eigenvector. And here the eigenvector can be perpendicular, can be not. But here professor mainly talk about the case where there are n distinct eigenvector, because that's the case that we are always interested in. And in that case we have like n1, n2, and 3 are distinct. Okay. And the word here can be chosen, it just meant that it doesn't have to be a unit vector. The eigenvector doesn't have to be the unit vector, because I would say this is, let's say, my eigenvector 1, and this is perpendicular to something else. But this is not an eigenvector. This is not a unit vector, which means they are not orthonormal. And that's what this want to express, that we can choose this to be orthonormal as well. Eigenvector, right? So that's about the first one. And the second one, this quickly ties into a new factorization that we have. So we have been learning so far, if A is symmetric, then we know that we can factor it in this form. So this is the eigenvector matrix, and this is the eigenvalues matrix, and these are the inverse of S. But knowing that we can actually choose the orthonormal eigenvector. So when we say we have that orthonormal column in each in the matrix, then we are talking about vector Q, right? That's the definition of the orthogonal matrix. Orthogonal matrix is a matrix which the columns are orthonormal. So here we can convert this one into Q, because our eigenvector are now orthonormal, and this stays, and this one also minus inverse. I mean minus 1 because it's the inverse. But another property from orthogonal matrix with orthonormal basis, of course, is that Q transpose equal to Q inverse. So we can have a new factorization, which is this, and this is really used. This one is really powerful, and this is called the spectral theorem. Spectral theorem, or in mechanics it is also called the principal axis theorem. Okay. Now, in the lecture, Professor Strang proved how the eigenvalues can be real. So let's just do that here. Okay, so we have done this, and we are going to do this next. Okay, let's do it here. So I have matrix, I have eigenvector, and I have eigenvalue. Okay. But we know so far that the eigenvalues can also be complex number. So it makes sense to me if I also do the conjugate of them. For example, if I do this, okay, then this is also makes sense, because imagine that here you have the component of I, A plus IB, for example, and here you have component, the conjugate of them. Okay, this is the idea of the complex conjugate, and this also makes sense, right? Okay, now we want to prove why this is real. Let's do the transpose of this transpose and this transpose. So you have x bar transpose A transpose equal x bar transpose lambda bar transpose. But now our A is symmetric, right? So you have x bar transpose A, now x bar transpose lambda bar transpose again, and I'm gonna multiply both sides by x. So I have transpose and x bar t bar x. Okay, now let's save this one. Now let's do some multiplication, also manipulating the first equation here. Multiply both sides by x bar transpose. So you have, let me change the color. So from here we have multiply by the x bar transpose from the left. Okay, cool. Now see that we now compare these two equations. We see that the left hand side are same. I'm sorry, this should be x bar transpose. I multiply this by x bar transpose on the right, so I have x bar transpose here. Yep. So I can now compare them, and I will get x equal to okay, and lambda is just some scalar, although it also is in a complex, it's just like one number. So I can move that here, and here I have like x bar transpose x, x bar transpose x, and this guy is always some value, right? Because what happens here is that a multiplication or a dot product between these and this. So this will give me the length squared, because a squared, this will be give me I squared b squared, and I squared is plus 1, so plus b squared ab. So this will be like the sum of each component, which is the a squared plus b squared. So what I want to say is that I can cancel them out. Okay, so now we end up with the lambda has to be the lambda bar. Just remove the transpose there because it doesn't matter. This is scalar, only one value, not a matrix. Okay, the only condition that this is true is that if we don't have the imaginary number. So for example, plus IB equal to I plus IB. This should not have the imaginary. So A equals to A plus IB, and the only thing this goes right is when this is 0. So this proves that our lambda is real values. So we finish this third point, And Professor Shrang, the lecturer, also mentioned about breaking down this equation, this new factorization that we have. So we will break down into, I still have some space, let's bring it here. So let's see what is happening inside this matrix. So I have Q1 until Qn, then I have all the eigenvalues in the diagonal. Here I have the transpose of them, right? This is the row until Qn transpose, this is in the row. So this is in a column and this is in the row. So what I have here in the end is that, like, I have this eigenvalues 1 times, imagine that this is multiplying in the column first, so I have this, and then I have this column times row. So this is relating back to how we multiply matrix, and one of them is doing the column times row multiplication. A quick example is that if you have like 1, 2, 1, 3, and then you have one, like let's say the identity, then you can break it down by saying 2, 1 times 1, 0 plus 1, 3 times 0, 1, the second column, the second row, right? So second column times second row, first column times first row. That's just a quick review. And then you add them and then you will have the result. So this is the same that happening here. So this is the column times the row in the end, and the lambda again is just a scalar. And then this is just another way to look at the spectral theorem, is that every symmetric matrix is a combination of our perpendicular projection matrix. You're saying now, wait, hold on, where is the projection matrix here? Why do you say it's a combination of projection matrix? So this is the projection matrix here, the Q times Q transpose, the Qn times Qn transpose. Remember that in the projection chapter that we're interested in the, for example, let me clear up some space here. Remember, so we have we are in the space of A, and then there is a B here, and we're interested in the projections of B into the A, which is the P here, and then the P is some kind of a ratio of A, and then the ratio itself is the A transpose B over A transpose A, and then this is also the bring back. So this is the X, right? The X is this part and the A is just here, and then we say we can, from here we can compute the projection matrix, which is moving A into the front, and then this is A transpose B over A transpose A, and we say that this is our projection matrix here. See the similarity between this and this. This is also A transpose, Q transpose, but now our denominator is 1 because these vectors are orthogonal. Yep, so that covers our fourth point, and in the next one I will discuss the last three. Thanks.